this lecture, we'll learn about the derivatives as a function. So from the previous section, we know the derivative definition f prime a is limit of h approaching 0 f of a plus h negative fa divided by h. So when we replace a by x, when a is replaced by x, we have this definition. F prime x is limit h approaching 0 f of x plus h negative f of x divided by h. Here the f prime is a new function and we call it as a derivative of the function f. So we are given a function f of x over 2 negative 1 half. We are asked to find a formula for f prime x. So let's do that here. First we need to write the formula for f prime x. F prime x is the limit definition, h approaching 0 f of x plus h negative of f of x divided by h. Now we want to make a note of the function f of x, which is the given function x over 2 negative 1 half. In the next line, we want to write f of x plus h. So wherever you have x in the function, you're going to replace it by x plus h. So this is x plus h over 2 negative 1 half. Now you want to plug in fx and f of x plus h back in the limit definition. So when we plug in, we have f prime x equals limit h approaching 0 f of x plus h is rewritten as x plus h divided by 2 negative 1 half. Then negative f of x is written as negative x over 2 minus 1 half. Now the entire function is divided by h. So the negative outside is distributed to each of these functions. So this is limit h approaching 0. We have x plus h over 2, negative 1 half, negative x half, positive 1 half divided by h. Now the negative and the positive 1 half gets cancelled. And we have two fractions in the numerator, which has a common denominator 1 over 2. So I'm going to bring the common denominator 2 and write the numerator as x plus h negative x. The entire fraction is divided by h. So we are adding these two fractions. And then when we add the fractions, we see that x and negative x will give us a sum 0. So all we have is limit h approaching 0, h over 2, the function is divided by h. Now you can take the denominator h to the top and you want to flip this. So you will write this as limit h approaching 0, h over 2 times 1 over h. Now you're good to cancel these h and you have 1 half. This 1 half does not have any constant h, so you don't have to plug in the limit h equal to 0. And this is your simplified answer and the final answer. So the formula for f prime turns out to be 1 half. In the next problem, you're given a square root function and you're asked to find f prime. So first write the definition of f prime, which is limit h approaching 0, f of x plus h, negative of the function f of x divided by h. Now you want to list f of x, which is the given function 1 plus x root. The next line you want to bring down f of x plus h. So x is replaced by x plus h and the new function looks like this, x plus h. Now you have f of x plus h and fx. You're good to plug these back into the limit definition here. So the limit definition looks like f prime x equals limit h approaching 0 square root of 1 plus x plus h negative square root of 1 plus x divided by h. Whenever you have a rational expression and you have the square root function sum or difference, the method is called as rationalizing. So you have multiply a similar term with a difference of sign. So you want to multiply here by square root 1 plus x plus h, square root 1 plus x. You did have a negative here in the problem, so you will multiply by a plus sign. Whatever you multiply in the numerator, write exactly the same term in the denominator. And once you choose the right choice of the multiplier, you want to read the pattern of the term carefully. The first term is a, the second term is b, a minus b, and the next term is a plus b. We understand that the product of a minus b and a plus b is a square minus b square, which is the difference of term. So you don't have to multiply it exactly by showing the multiplication of each term or foiling it, but rather you can write the difference of the term, difference of the squares. The first term is 1 plus x plus h. You're going to square this term, negative. Second term is 1 plus x root, and again square, divided by the denominator, which is h times square root 1 plus x plus h plus square root 1 plus x. Now we know that the square of a square root is just the term. So cancel those and bring down the other terms. You have 1 plus x plus h from the first term, and you have a negative which is common to both the terms, so you want to multiply the negative. So it's negative 1, negative x. And then you have h times the sum of the square root terms. Now you read the numerator carefully. X negative x cancel, 1 negative 1 cancel. You're good to rewrite the numerator as limit h approaching 0. You have h divided by h times the terms in the brackets. Now you have product of term in the denominator and you have product of terms in the numerator, so you are good to cancel these h. After cancelling h, now you are good to plug in h equal to 0. So you have 1 plus x plus 0 square root, and then you have plus 1 plus x. Now you have simplified this for one last time. This can be rewritten as 1 over 2 times square root 1 plus x. And this is your final answer. The next example, you're given a rational expression. You're asked to find the derivative using the definition. So let me write f prime x is limit h approaching 0 f of x plus h negative of the function f(x) divided by h. Now you want to write the function f of x, which is the given function x over x plus 2. Now try to write f of x plus h. So wherever you have x, replace it by x plus h. So this becomes x plus h in the numerator, denominator becomes x plus h plus 2. Now that you have the function and its increment by h, you're good to plug these back in the limit definition. So you have f prime x equals limit h approaching 0 x plus h divided by x plus h plus 2 negative x divided by x plus 2. Entire fraction is divided by h. Now in the numerator, you have difference of two fractions with a different denominator. So you want to make a common denominator. So multiply x plus h plus 2 for the second fraction and multiply x plus 2 for the first fraction. By doing so, you have a common denominator. Now you're good to rewrite the terms. The numerator becomes x square, multiply them out and write in a neat order so that it's easy for you to add the terms. X square, x times x is x square, x times 2, 2x, h times x, hx, h times 2, 2h. Similarly, x is multiplied to all these three terms. X square, xh, write that below hx, and then 2 times x is 2x. And you have a negative sign for x, so every term gets a negative sign, so write negative. And this term is divided by x plus h plus 2 times x plus 2. Still, this is the numerator of the entire fraction, and this entire term will be divided by h. So this is this denominator. Now cancel these negative x square, negative 2x, positive negative terms. So all you have is limit h approaching 0. You have 2h in the numerator and x plus h plus 2 times x plus 2. This is the fractions numerator, and you have one more denominator for this, which is h. Now you're going to take this h in the denominator to the top, which means you're going to flip it, write it as a multiplication term. So this is 2h divided by product of terms times 1 over h. At this step, you're good to cancel the h. And now you have 2 divided by x plus 0 plus 2, h is 0, and again x plus 2. So you have 2 divided by x plus 2 twice, so you write it as x plus 2 square. And this is our final answer. In the next part of the question, you are asked to find the domain of the function. So you want to write the function in the problem f of x is x divided by x plus 2. Whenever you are given a rational expression and you're asked to find the domain, you always start with the denominator term, saying that the denominator term cannot be equal to 0. Now solve for x. All you say is x cannot be equal to negative 2. So on the number line, you leave out negative 2, whereas you can consider all the other points on the number line. And you say that the domain is all the points other than negative 2. So you're going to write it as domain, start from negative infinity all the way up to negative 2, stop, union, start from negative 2 all the way up to infinity. So it's all these points other than exactly the point negative 2. Next, you're asked to find the domain of its derivative. So write the derivative of the function f prime x, which is 2 divided by x plus 2 the square. This is what we found by the definition of derivative. Similarly, start with the denominator term. You say that the denominator cannot be equal to 0, which means x plus 2 cannot be equal to 0. Solve, all you have is x cannot be negative 2. So the domain is still the same as the previous discussion. It is not negative 2 but all the other points. So you can say domain of f prime is exactly same as the domain of the function f. Similarly, you can try this problem using the definition and find the domain of the derivative and the function. In the next example, example 5, you want to match the graph of each of these functions a to d with its derivative graph below 1 to 4. So we have 3 rules to look at. So let me list the rules. So you will look for number 1, horizontal tangents. The meaning of horizontal tangents is f prime x, the derivative is going to be equal to 0, which means the slope is 0 for the line. So you will look for f prime x, which passes through the x-axis at the same points. In the next line, you will look for the corner points of the function, which means you will look for f prime x is not defined. So whenever you see a corner point, you can say the derivative is not defined. In the third step, any interval where the function f of x has a tangent with a positive slope or even it can be negative, the graph of the function f prime is going to be positive or it can be negative. So these are the definitions you will look for in order to match A to D graphs to 1 to 4. So all these A, B, C, D graphs are called as the function graphs f of x, and all these 1, 2, 3, 4 graphs are called as the derivative graph f prime x. So now let's read the graph A carefully. This is a function graph f of x, and you see that for the first half of the interval, or like let's do the horizontal tangent first. You have two horizontal tangent here. You can say this f prime is 0 here, the slope is 0. You are able to draw a horizontal line. F prime is 0. And in this part of the curve, you see that you have a negative slope. This is an f of x graph, so you see that it's a decreasing. So you can say f prime x is less than 0. Again, in this part of the curve, you can see the function is increasing. So you say f prime x is greater than 0. Then again, in the last part of the curve, you have f prime going down, so it's less than 0. So f prime x less than 0 can also be written as the slope. To start with, you're going to read the interval in this direction, left to right. You started with a negative slope, then it becomes 0. Then the slope becomes positive. Then again it becomes 0. Then it becomes negative. So f prime graph, the Roman numbers 1 to 4, is the graph with the slopes. So you will look for a graph where you have this negative 0, positive 0, negative pattern of the slope. And you see that graph here. You read this graph too carefully. X-axis is x itself. Though it's written as a y-axis, read this carefully as an f prime graph. So it's an f prime axis. So here the f prime value is negative. It becomes positive, and in between it's 0. Then it's still positive. Then it becomes 0. Now f prime becomes negative. So read the graph of this function from left to right in this direction. It is negative 0, positive 0, and then negative. So the first graph A matches with the f prime graph 2. This is your function graph, this is your derivative graph. A matches with 2. Similarly, let's do one more graph, graph C. Or let's do B. In the graph B, you have sharp edge here at 2 points. So this is the second point to be noted. Whenever you have a corner points on the function graph, your f prime graph at exactly a similar point on the x-axis, the f prime graph will not be defined. So you look for a graph where you see the f prime, the derivative is not defined. And it turns out to be exactly those similar points on the x-axis, these 2 points. On your graph 4, you're seeing a jump in the function. You're seeing a jump at both the points on the x-axis. You have a discontinuity in the graph. So you're going to say that this graph 4 is going to match with the function graph, which is P. Similarly, I want you to try out the other 2 graphs for C and D. Try this before you look into solutions on the blackboard, and then try to match it with 1 and 3 of the graph. Next is definition of the differentiable function. A function f is said to be differentiable at a if the derivative exists. It is differentiable on an open interval ab if differentiable at every point on that interval. So a function f is differentiable at a, then the function will always be called as a continuous function. So there are 3 ways for a function f not to be differentiable. The first case, when you see a corner point, or when you see a discontinuity, the function is discontinuous, or when you see that you can draw a vertical tangent at some point, say A, you're able to draw a vertical tangent. So at all these 3 types of graph, the function is said to be not differentiable at the point A. So we have an example here, the absolute function. The question is asking you, is the absolute function differentiable at x equal to 0? I want you to draw an absolute function graph. This is the absolute function graph. And you see that you have a corner point here. And the very first example on the top shows that whenever you have a corner point, the function is not going to be differentiable at that particular point. So you specifically say the absolute function is not differentiable at the corner point. Now you have been given 4 graphs. You want to say if the function is differentiable or not. The very first graph, you see that you have a corner point at x equal to -4. This corner point is here, so the function is not differentiable there. Similarly, at x equal to 0, here you're seeing a discontinuity in the graph. So x equal to 0. And at x equal to 2.5, you're able to draw a vertical tangent. So at these 3 points, x equal to -4, 0, and 2.5, you can say that the function is not differentiable, whereas the function is differentiable elsewhere, not just at these 3 points. Let's move on to the next graph. At x equal to 0, you're seeing that the function is not continuous, and it is discontinuous. X equal to 3, you have a corner point, and you always move on from left to right when you read the graph. And so x equal to 0 and x equal to 3 are the 2 points at which the function is not differentiable. Similarly, I want you to try these problems with a similar definition, the first 3 definitions of the graph. That should help you to identify whether you have a corner point or you have a jump discontinuity and so on. So we'll end this lecture here.